Now let's look at how we can evaluate exact values of inverse circular functions given a composite function. For instance, the tangent of the inverse sine of negative 2/3. We're going to evaluate this geometrically by drawing reference triangles that will allow us to determine the answer. So we start from the inside where we're looking for the angle that produces a ratio of negative 2/3 for the sine function. So I will draw a coordinate system, and then I'll draw a reference triangle whose opposite is negative 2 and hypotenuse is positive 3. Since the inverse sine is restricted to quadrants 1 and 4, that means my reference triangle will have to be in the 4th quadrant. So a hypotenuse of 3 and an opposite side of negative 2. That would give me this angle here. Now, once I have the reference triangle, I need to find the tangent for that reference triangle. So there I need to determine what this adjacent side is going to be by the Pythagorean Theorem. So 3 squared is going to equal negative 2 squared plus the adjacent side squared, which means that our adjacent side is going to be 9 minus 4, or the adjacent side squared, or 5. So the adjacent side is the square root of 5. We know it's positive because we've had to draw our triangle here in the 4th quadrant, which means that our answer for the tangent, which should be opposite over adjacent, which means we should get negative 2 over the square root of 5. Let's look at another example. Here we want to evaluate the sine of the inverse cosine of x geometrically to find the answer in radical form. So again, let's start with a coordinate plane. Now, cosine of x, if we use our SOHCAHTOA, is adjacent over the hypotenuse. So we can write x as a ratio of x over 1, which will give me my adjacent and my hypotenuse for a reference triangle. We're going to draw that reference triangle in the 1st quadrant. We'll label the adjacent side x and the hypotenuse 1. And to figure out our 3rd side, the opposite side, we're going to use Pythagorean Theorem again. So 1 squared is going to be x squared plus y squared. And if we solve for y, we'll see that y is the square root of 1 minus x squared. Since we're asked to find the sine value, then that would be opposite over hypotenuse and give us an answer of the square root of 1 minus x squared. Let's look at one more. The cosine of the inverse cosine of x. Again, we'll draw our coordinate plane, label our adjacent to be x and our hypotenuse to be 1, meaning we're looking at this angle. And if I want to find the cosine of that angle, well, it's just going to be x. So the cosine of the inverse cosine of x turns out to be just x. This illustrates a fundamental property of functions and their inverses. If we create a composite function between a function and its inverse, the operations involved in each of those functions cancel each other out, and we're left with just the independent variable x. All right, let's recap what we've learned over the last two videos. How do we plot an inverse trigonometric relation graph using parametric relations? Well, we take the original function, sine or cosine, and instead of placing that in the y line of our parametric function, we place it in the x line, and in the y line we place the parameter, t. How do we choose principal branches for the inverse trigonometric functions? Well, we have our 5 criteria. Must be a function, must use the entire domain of the inverse trigonometric relation, and then our optional criteria in decreasing level of priority. It should be one continuous graph if possible. It should be centrally located near the origin. And then if there is a choice between two possible branches, use the positive side. What are the domains and ranges for the inverse trigonometric functions? Well, we summarize those on a slide that talks about each one of those for your reference. How do we calculate exact values of inverse circular functions? We draw the triangles that produce the ratios necessary. What is the property that discusses the composite of a function and its inverse function? Well, that property is the fact that when we create the composite, the operations cancel out and we're left with the independent variable x. And that's provided that x is in the range of the outside function and in the domain of the inside function. We can't come up with a value if x is not within the domain of the inside function, and then that answer has to be in the range of the outside function.